Now welcome back to the class. So we want to write the code, the Verilog program to describe our design. So we have two parts. Remember, we have the data path, this one, and also we have the control unit to be designed. And we want to simulate the design whether we get the result that we want or not. Okay, so we have the quarters 2 here. So we need to have this here so that we can write the code for this. And let's create the new file here. Let's have a new project here. Example 6.3. Right. So we want to design the DU first. DU of example 6.3, and use this folder and this, and there is no, now we will use the device, the cycle 2 device, because we want to use the later on when we use this multiplier and the adder. This is the internal IP circuit from the quarters 2, so it's better to have the hardware or correct device selected here. All right, the one that we have, and this is, so we have module, and because we want to describe the register, of course we need to have a clock. We need to have the reset to reset the register, and we have this the input and the remember our input is in the form of control vector now, so we group this signal together. So in this case, let's name this signal as CV, control vector, and now we have all the control vector here. The name is CV. We have the input A, B, C, D, E. So we have A, B, C, D, and E. And again, for the simulation purpose, we want to see what is inside R1, R2, R3, and R4. So we can make this as output or list in the output port as well. So we have R1, R2, R3, and R4. All right, and we have input, which is the 1-bit input. Reset, of course, and the another input, which is the data. Let's say our data is 8-bit, right? A, B, C, D, E are 8-bit in size. So we have A, B, C, of course D and E. all are 8-bit. Any other inputs that we need to have? Yes, the CV. The CV we have 12-bit, 13-bit. In this case is 13-bit, remember? So we have 13, 0 to 12. So should be 13. So right, 12, 0, and name is CV. And we have output. In this case is 8-bit, and we have R1, R2, R3, and R4. Okay, and we have this signal, right? These are 4 signals here, and this one of course need to declare as reg as well, because we will describe the register using behavioral modeling later on. And this one is reg, and of course the size is 7-bit, 8-bit. So let's name this as multiplication out. Out. This is add 1 out. This is add 2. So we can use this one as 2, and add 3 maybe. Okay. And we need to define our control as vector as well. Control vector, right? The name for this one is better to use this name, easier for our code later on. So we can have this wire for type for LD1, LD1, LD2, and we have LD3, and we have LD4, and this cell 1, cell 2 is 2-bit, so we need to declare in 2-bit, but this one, and this one are 1-bit, so we can list here. Cell 3, cell 4, cell M1, cell M2, and cell A, right? All are 1-bit, and you have the 2-bit, which is the cell 1 and cell 2. So these are 2-bit. All right. Now we need to assign this to the CV. Right. So we can use assign. We can start with SEL1, just like this. SEL1, bit number 1. Okay, is bit number 12 in this case. So SEL1 bit 1 is actually CV. Okay, actually CV 12. Okay, right. So this one is bit 12, and we also have cell 2. Not yet. cell bit number 0, which is CV11, right? And we have cell 2, okay, just like this, cell 2, bit number 1, cell 2 bit number 1, which should be bit number 10 in this case, and we have cell 2 bit number 0, this is 9, and we have after cell 2 it should be cell 3, and we don't have this, we only, cell 3 is only 1 bit, and this should be number 8, and we have 4, should be number 7, we have cell M1, should be number 6, we have M2, should be number 5, we have cell here A, should be number 4, we have after cell A, so it should be this, right? Cell A should be L1, D1, LD2, LD3, LD4. So I'll just go back to this. So we will have this should be LD1 first. LD1, this is number 3. This should be number 2. LD1. It's 7, 6, 5, 4, 3, 2. Cell, oh no, this is LD1. This should be LD2. And we have LD3. This is number 1. And the last one will be LD4. This is CV0. Right? So done for the control vector. So now we want to create this, right? So in this case you can have one module connected to this multiplexer, or you can create a module that comprises of register R1 and also SEL1, the multiplexer, in one module. Here this is one module, this is another module, and so on and so forth. So in this case I will combine this R1 and this multiplexer in the same module. So so let's have this as R1, so you can have always, and clock, and set, and if reset, we can say that the output here, which is R1, should be equal to 0, else if this LD1 equal to 1, so the output R1 will depend on this select input. So this select input, we have a multiplexer, so we can create the multiplexer here. We can use if else, or we can use case statement in this case. So we can use case statement, which is this one, SEL1, right? So should be 2-bit. 0 0. So if 0 0, odd 1 will be equal to what is that? If 0 0, so it should be this, yeah. So this is this add 1 out, right? So but if 0 1, we can have if 0 1, we can have this, right? So this is the multiplier, so it should be this one. And if 1 0, it should be A, right? 1 0 should be A. And the last one, if 1 1, so this one 1 1, so 0, we can have a 3-state buffer, but if there is 3-state buffer, we need to have extra circuit, right? So maybe we can avoid that by using set this to don't care. So 8-bit H, right? And that case, so that will be odd one with this multiplexer. So now we create the R2. So R2 should be same as this one, except that the name of the signal and the input is different. So we can actually use this one. And now we have R2. And of course, here will be the R2. And this is LD2. And this is select 2, of course. This all will be number 2. Number 2. And look at this. If 0, so should be from the multiplier. So should be from this. If 0. No. If for R2, if 0 is from, yes, from multiplier. Right? 0 is from multiplier. If 1 is from this, yeah, which is this one at 2. Or if 0 1, and if 1 0 is B, so this should be B. And done. Right? Now R3. R3 is, we have 2 to 1 marks here, so no need to use case statement for this one. We can use if and else statement. So but from here to here, we can actually use the same code, except that the name of the signal. So this should be R3, and this is R3 and D3. So here, if LD3, but we need to have this one, if 0, so it should be C, if 1 should be E, and this 0 and 1 is SL3, so we can have another if SL3, if SL3, so R3 will be equal to, or maybe we can, this is 0, so not SL3, 3 should be equal to C, right? else say that R3 should be equal to E. All right. And for the R4 should be similar to this. So we have R4, and this is number 4, and this is number 4. And the select here is SEL 4, and this should be 4, and this should be 4. So if select 4 equal to 0, so it is D, and if it is equal to 1, it should be this signal, and the name must be this one. All right, done. Now this register and also the multiplexer at the input is described here, and now we want to describe this multiplier, so we can use behavioral modeling to model this. So let's do this using always block, and let's see what is the should be in the sensitivity list. So it should be the input, which is this SEL M1, M1, SEL M2, and all of this signal, which is this one is R4, R3, R1, and R2. So all of the signal R1, R2, R3, and R4. And for this, we can actually create this one by one, or we can actually combine the signals. All right. So how to combine this signal? We can use concatenation features. So that we can use case statement. All right. So we can use case statement, and we combine SEL 1 M1 with the SEL M2, so that we can have 4 possibilities, right? Because this is our circuit, so we should have 4 possibilities for the output here. So the first possibility is when this, right, 0 0, both this one and this one are 0 0 0. So what happened? So if 0 0, okay, the output here should be this. This should be equal to this one multiplied by this one. So this one is R4, and this one is R1. So we can say that this is R1 multiplied by R4 when 0 0, and when 0 1, right, when this one is 0 and this one is 1. So 0 1, we can see that this is still R4, and this one is, if 1, this should be R2. So it should be R2 multiplied by R4. And if 1 0, should be R3 here, and 1 0 should be R1 multiplied by R3. Right, 1 should be R3 here, and 0 should be R1. So R3 multiplied by R1 or R1 multiplied by R3, the same thing. And the last one is when both are 1, 1. So 1 is this one, should be R3, and 1 here should be R2. So R2 multiplied by R3. Right, so this should be all the possible output here. And now we should have the adder number 1, adder number 1, and we can use this. The sensitivity list in this case is of course this one, and you have R1 and you have these two, R2 and R3. Right, so so here you can use if else statement here. So we can have if cell A equal to 0, right? So if cell A equal to 0, the output here is at 1 out. Should be at 1 out here should be equal to R1 plus R2. R1 plus R2 here. Else means that if select equal to 0, equal to 1, so means that this will be always R1. So the output should be R1 plus R3, right? So that will be this one. What about adders number this and this, number 2 and number 3? So this one is easy. Here too, we can use always blocks or even data flow modeling, yeah. But because this we declare as right already, so we need to use the always block. So the input for this is actually R1 and R3. So the output is actually this one. Should be equal to R1 plus R3, and we have that. And the last one is adder number 3, so it should be similar to this, except that this R3, which is this one R4 plus R3. So we have R3 and R4. So this one is R3 plus R4 for that. So observe that I use this operator plus. This means the adder, means that we instantiate the adder, all right, using the internal library for this design. Means that we not designing our own adder, yeah. This one also the same, means that we use the internal multiplier rather than designing our own multiplier. Okay, so should be done for that. So we and module here means that done for our data path. We can save this, and the name is this. Try to synthesize the design. Hope that we don't have error that, but we have 5 error here, and we can see here what is the problem. So syntax error should be easily fixed. And let's say what is that? We should not have this, right? For always block. Already declared in the, is it name is different, SEL, and all because of the previous error. Maybe we try to synthesize again. Or we have many errors. So let's see. Can resolve multiple constant driver for net disk. Yes, because we use the same name, should be AD the out, yeah, because of the copy and paste from this, so should be a tray out for this one. And again, try to have, so we have 2 warning. What is that warning? So we have this R1 already exists. What is that? Oh, we have 2 R1, so no need to have that. Okay, it should be that thing, and yes, it's good, right? So this is the data path. So we can try to simulate the data path, but in here I will simulate the whole circuit instead. Yeah. So before that, so we need to design our control unit. All right, based on this. Yeah, this is the design for our control circuit, control unit. All right, so we need to design this and need to generate this CV, and how to generate this CV must be from this. This is our CV. All right, so you need to go back to this, and yeah, we want to design this. So again, we need to have a new one. Create a new folder. The name is CUEX63, and okay, the name, and let's have a correct device. This should be finished. Verilog, the name, and the port list is should be based on this. All right. So let's create this. So of course you need to have a clock, the reset, and the CV, this one, CV, and yeah, actually we have another two signal, which is this X done and Y done. So this is the output to the from the control unit as well. X done and Y done here. All right. So for that, we need to have that X done, Y done, and let's have another output, the state. This one just to observe the state transition when we do simulation later on. So we can have that. Input so should be the clock and reset. And we don't have any other input, so just list this output, which is 12 to 0, 13-bit for CV. And of course, we need to use rack, right? And we have to have output this two, X done, Y done. Right, and of course we need this one, the state. And the state, how many state we have? We have 4 states, so the size should be 2-bit, just here. So it should be the 1 0 state, and done. And we need to define this also. The name is next state. So and this one should be rack also, rack, and this one also, the type should be rack. Next state. All right, and of course the state name using the parameter declaration parameter, and the size is 2-bit also, and we start with S0 equal to 0, S1 equal to 1, S2 equal to 2, S3 equal to 3, right? Done. And we define our state register already here. Okay, so this one, the state register, so easily defined using always block, and this is negative H triggered, and positive is clock reset. So if reset, we know that the state, the output here is state is equal to 0, or in this case is S0, else state is equal to this next state. All right, so that should be done. And this one is to define the next state and the CV logic, or we call it output. Okay, so for that, we need to look at this. So we have the input for this is this state, and also this one also the state, means that the this signal and this signal is depend on this state signal. So we can use behavioral modeling, and should be state, yeah, the sensitivity, because only depend on this signal. And now we can use case statement because we will have many case here, 0, 0, 0, 1, 1, 0, and 1, 1, or S0, S1, S2, and S3. So you can have case state. So if state to S0, so we have many statement here. If S0, so what do we do? So we need to do this. We need to output the CV to be 140F. Yeah. So we have CV should be equal to 13-bit, and this is hexadecimal. 140F, 140F, right? And next state, yeah, this one, next state. What is that? So it should be next state should be equal to after S0 should be go to straight away go to state 1, S1 here. So we go to S1, and we need to define the x done and y done also. So should be x done should be equal to 0 in this case, and y done should be equal to 0 also in this state, and should end here. And we can use the same code here, except that this is S1 and CV is now for S1 is this, yeah, 028D. So we can have this 028D, and the next state should be S2, and S2 S1. So y done and x done is not 1 yet, so should be still 0, should be no problem. And the next one is S0, yes. Okay, so we can do this again. We have another one, and now is 013E. So we can have 013E, and the next state will be S3. And now S3, what we have here is y done equal to 1 already. So we have y is done. So this one should be equal to 1. And the last state, should be S2. Should be S3 here. And here should be this 0848. 0848 hexadecimal. Next state should be go back to S0 when we finish to have a new one. And here we have y done, x done equal to 1 already, and should be n here. All right. Any other things that we missed? No. So this one should be n case, and should be done already. Done here. Oh, not done. In module, right? So this should be our control unit that represent exactly this one, and the output for the control unit is based on the RTLCS table here. All right, so now we want to save this and see what if we have any error in the code, right? We have warning, And let's see what is this warning. Warning is truncated value with size 2 to match size of the target. Means that the size here is not correct. Okay, so let's see what is the problem here. So here, the next state, maybe we have the problem with this. Yes, the next state should be 2-bit here, right? So this must be 2-bit because here we are 2-bit, right? So should be okay now. Okay, we still have 3 warning, and this warning is output pin are stuck at VDD or ground. So C3 stuck at VCC means that always 1. All right, CV3 is always 1. So what is CV3? And let's see, CV3, yes, always 1. So this should be no problem for us, right? Because in our design, we want this to be always 1. Okay, always load data into R1 for every cycle, so should be no problem. So we can ignore that warning. Now we want to integrate this into a single design. All right, CU and DU. So we can have a new design now. We can have okay. So this is the folder, and here, let's see. And of course, now we want to use this in our design, and of course this one. So need to add the device. We can finish here and have a new Verilog file, and the name is module, and this, and here what we have is the connection between the two. So let's have this. So now you need to have something like this. You have a CU and you have your DU. Okay, so and in your CU, of course, you have a clock, which is a negative edge triggered, and you have the reset signal to the input, and you don't have any other inputs for this, but you have the output. The name is X done and also Y done, and you have the CV, all right, which is 13-bit to control this DU. Okay, and this DU you have the input, which is A, B, C, D, and E. And for simulation, we want to see what is the value inside DU. So in our design, we have do this, right? So meaning that R1, R2, R3, R4 have a connection to the output as well. So we can have that, which is 8-bit. All of these also are 8-bit. We have R1, R2, R3, and R4. All right, and of course we have the for CU. When we look at the CU, we also have this state for another one to see the state. So that will be the list of the port that we need. Yeah. So if we have this, so we need to have, and of course this one, we have a clock as well, which is positive edge, and we have reset also. So we have clock, we have reset, use the same name as the submodule, right? We have input A, B, C, D, E, right? And what else? Output R1. We have the output R1, R2, R3, R4. We have another output X done, Y done, and we also have state. This one, state. All right, all of this are defined already. So we can close here, and we have input. This is clock and reset, and we have 8-bit input. A, B, C, D, and E. We have output X done, Y done. We have output the 7-bit, 8-bit, R1, R2, R3, and R4. Now we have for the state one, 2-bit, and this should be 2-bit. 2-bit, and we have this CV must be declared as wire, and 13-bit 1220 CV. That's it. Now we want to instantiate our DU and CU here, so we can instantiate the CU here. We can use this one because the name of the port is the same, so easily copy it to this, and let's say the name is CU, right? And the DU, the name is the same, so we can just copy this to this, and let's name this as DU, and here is the port and module. All right, so now we have this already in this, and just save this, save, And now try to synthesize and see whether we have any problem or not. No. Okay, just one warning for this license. Should be no problem now. So we have that. And now we can write the test bench and see the output for this design, right? So let's have a test bench. One nanosecond to 1 nanosecond. Module name is let's name this as CUDU EX63, maybe attachment here. Okay, so this will be based on where is it, this, right? So we will use the same input and output as this one, so we can copy this into this so that we can have this, and this, remember, need to use rack. Okay, and this also can be rack, must be rack. This should be wire, this should be wire, and the last one also should be wire. And now we want to instantiate our design to be tested here, and this is the design, so just instantiate this one into this. So to instantiate, it's easy. So we can have this one is the name is DUT, the design and the test. So this is the our design and the test, and now we will create the simulation. Right, we can want to monitor this thing so that we can see the output. Right, so we want to look at this, all of this, and clock, and this can be in the form of binary. This one is binary, and this one can be in hexadecimal or decimal is better. Decimal, and this one should be in binary. Should be in binary, and the state in decimal should be no problem for that. And this should be mapped to this signal. Okay, done, and we set the clock to be 0 at first, and we can end this, and we create the clock using this, where it's toggle the clock every 10 nanosecond. All right, so that we have period of 20 nanosecond, and we have the input stimulus or input vector here. So at time 0, maybe we reset our design to 0, right? So reset equal to 1 means that we reset our circuit, and we set all of the input to be 0. Okay, and maybe the next 10 nanosecond we set to 0 now, not reset, and we change this value to maybe a equal to 1, b equal to 2, c equal to 3, and d equal to 4, and e equal to 5. And we run for another 100 nanosecond and stop the simulation here. And need to end this and module here, right, and see what happened. First thing is we need to save this using this name. Should be inside this CUDU. Okay, so this is in synthesis, so we don't have any syntax error. Means that the design is good. So now we want to simulate, and of course we need to do some setting here. The name, the file, not in here, but in should be in CUDU. Now here, this is the file. Add and OK. Okay, click OK here. Then we can run the simulation, RTL simulation, and see what is the output. All right, we have error here. Cannot load this CUDUX3TB, means that we have a setting. Let's have a new one. I mean, the file name is, where is that? So it should be this one. Okay, so let's see this, add, OK, and click OK again. Okay, and try to run the simulation. Okay, so we have, this is the value that we set actually, right? And when we look at the waveform here, okay, so we don't have the correct output. So what is the problem? Maybe at the clock is not correct because the clock is not changing. So let's go back to the testbed file. Yes, this is wrong. Should be clock and not clock, right? So again, need to do the simulation. And now we have the output here, right? And we can see here when x done equal to 1 at state 3, the our output is in, if you look at this, our output x should be in R1 and y should be in R2. Okay, so this is what we have when we are at state 3, state 2, y done equal to 1. So means that y is available in R2, so R2 equal to 28. All right, we don't know that this is correct or not, but y is 28 and state as 3 and x done equal to 1, and means that it, x is available in R1. All right, so R1 is equal to 30. All right, or we can see in this waveform here, maybe we change to unsigned so that we can see the number. So here we can see that this is the state, so state 0, state 1, state 2, state 3, and go back to 0. At state 2, we can see that this is y done equal to 1 already, and we have this available in R2. So here y done equal to 1, and this is available in R2, so we have 28. So y 28, and let's see, look at our equation. So we have we set before this as a equal to 1, b equal to 2, c equal to 3, d equal to 4, and e equal to 5. So if you look at this, if we use this value in y, so we can have y equal to a, which is 1, plus c, which is 3, multiplied by c, which is 3, plus d, which is 4. Okay, so this is 4 multiplied by 7, which is 28, right? So y should be 28 if the input is this. And we can see that y here is in R2 is 28, which is correct in our case, right? But in later state, yeah, when x is available here, x done equal to 1, and this is the result in R1 should be x, yeah, x is 30. So using the same value, so we can see that here x should be equal to e is 5 multiplied by 1 plus 2 plus 3, which is 5 multiplied by 6, which is of course 30. So we have the output equal to 30 in this case. All right, so meaning that our design is most probably correct because we have the correct output here. So you can test for other input combination for A, B, C, D, E, and let's look at the output, whether you can get the correct output or not. All right, so this is for this number 1. All right, so although we have here number 1, you need to produce the data path only, but in this example I show you how to design the data path, how to describe the data path in Verilog, and also how to design your control unit and in Verilog, and how to simulate your design, right, to realize this. And for the next video, we will try to answer this number 2, all right, where the design is now constrained, all right, and we will apply the cost level restructuring to the equation x, all right. So this x, later on we try to uh, rearrange this equation, all right, so that we can minimize the hardware usage. And also the design is constrained to only one multiplier and one adder, right? So now what happens if the design now is not allowed to have uh, three adders like this? All right, means that you now can use only one adder, all right, instead of 3 like this. So 3 addition simultaneously like this is not allowed. So what to do? So we will look at that example in the next video. For this video, thank you. See you in the next video.